started. Welcome everybody to the Merritt Library. So nice to have you here. I want to first acknowledge that we are gathered this evening on the traditional and unceded territory of the Inglekatun and the Sioux people. We offer our respect and our gratitude for the opportunity to work, learn, and enjoy each other's company this evening on this land. We're delighted to have Al Horn back in the library. How long has it been, Al? Like 15
It's been a few years, yeah. Quite a
10
few,
years,
I'd say, at
15
least
years.
8 years or so.
So some of you probably were at Al's previous lectures. He did a series on Alexander the Great, and he did one on ancient Greece. And I understand they started off as just a few, and then they grew into like 3 years worth of lectures. So
10.
Not sure if that's going to happen this time.
10 years.
Yeah.
10 years.
10 years. Oh.
Yeah,
okay.
10 years.
10
yeah.
years.
Yeah.
Oh my gosh.
I was a young man then. I was in the youth of the earth, you know.
Anyway, Al's taken a kind of different direction with this series of talks. He's put an absolute ton of research into, as he always does, into his presentations. He's taken on a very ambitious task to try and cover such an extensive period of time in 5 lectures. But he's confident he's going to give it a good shot. But I'll let him explain how it is that he's decided to take this path into a more scientific direction based on his lifetime love of science. So over to you, Al.
Thanks. First thing to do is thank people. Okay, when you're in doubt, thank people. I've been trying to figure out, ever since I decided to do this crazy thing, how I was going to start it. I haven't totally made up my mind, but it's all going to unfold and be just fine in the next hour and a half. So first thing, I thank Claire. If it wasn't for her, we wouldn't be here. This wouldn't be happening. So I'll tell you in a minute what happened 2 years ago, but I want to finish and also thank you, because if it weren't for you, I know it's a cliche, but if it weren't for you, this wouldn't be happening either. And weren't for the audience and the library people. I don't know about you guys, but everywhere I go, every library I've ever been in, I instantly feel at home. I don't know if you guys feel like that at all.
Yes.
But I go in the library and I somehow think, these are kindred spirits. They've got to be, you know? And just looking at all the books, I mean, I can't help it. I love knowledge. That's what I do for fun, is I learn stuff, believe it or not. That's not crazy as it sounds. So, I like libraries, and I'm really happy to be here, and that's my way of saying, hey librarians, thank you very much for being here and for everything. You're really nice people. And Denise, like I couldn't have done it without her. I know nothing about electronics. She does all that stuff. She takes care of everything. I just sit around and learn stuff and get crabby when things don't go right, and she's the one that goes around and makes everything work. So thanks a lot, hon. Do you guys ever read The Wind in the Willows? How many people read The Wind in the Willows?
Several times.
Okay. I love that book. Now, who do you think my favorite character? Remember, there's Ratty. Remember? There's Ratty. There's Mr. Badger. I liked him. He was cool. Like he was tough, like my grandfather, but he was cool. So I like Mr. Badger. My favorite character was Mr. Toad.
Yes.
Remember Mr. Toad?
Yes.
Right? And the reason I'm thinking of Mr. Toad is that Mr. Toad got all these crazy ideas, remember? First it was like motor cars or caravans or trains, right? He was always going off in these tangents. And that's what I want to thank Denise for. I've been kind of a Mr. Toad, and I've been getting all these crazy ideas. I want to do this, I want to do that. When I decided to take up fishing, which is the reason we moved up here, she bought her own boat, rod, roll, the whole bit, was out there with me. So what I'm trying to say is thank you very much. And if it weren't for you, well, I wouldn't have had nearly such an interesting life. So, you probably, I'm going to have to sit down every now and then, or I might. I'm not used to being on my feet. Anyway, where was it? Okay, I got a piece of paper that I was waving about, and, there it is, to remember what to say. So, what's this going to be? Okay, what we're going to do is we're going to look at the history of life on Earth. And what I was going to do first was I was going to start up at the beginning. Now, what happened was I walked in here 2 years and 3 months ago. You don't happen to... Do we have that piece of paper in here?
It's there, baby.
Oh, shoot. Oh, this is it? This is a historical document. So Claire was over there, minding her own business. This was a library thing where people were meeting. And okay, you can see it. So this is February or January of 2023. It seems like a long time ago. But anyway, I walked in, fell into a conversation with Claire, and the next thing you know, I've seized this piece of paper and written this out. And that is that. So the poor woman is standing there. I don't know, she's probably never met me before in my life, right? She doesn't know who I am. And this maniac comes in and he goes like this, and he says, there!
And it was just spewing out of you, Al, just spewing.
Sort of like now.
So, I don't know, I'm apologizing. I don't know what happened. Something came over me. It was just like, you asked me a question, something started to come out of my mouth. It was like a dam broke. And then after that, okay, how many people have seen The Matrix? Okay. Remember that part of The Matrix where Neo has that sliver in his mind? It's like a sliver in your mind, Neo. Do you remember that? Jeez. Okay, anyway, there was a sliver in my mind. I thought these allusions to movies were really going to be a winner, but they're not working out. Anyhow, I came in, talked to Claire, wrote that out. That put the idea in my head that, well, after that I couldn't get rid of it. And then the other precipitating thing was, I was in here one day, and I said to Denise, go away and come back in an hour, please. So I got this little book. I didn't see it there today. It's by a guy called Andy Knoll. He's a good writer, and it's about the history of the Earth. So I sat down, and I thought, well, I wonder if I've learned anything. Excuse me, I said, I'll talk to you. I wonder if I learned anything. So I read this book. I said, give me an hour. So I took an hour, sat at the table right over there. Denise came back an hour later, and I stopped reading. I'd read 68 pages. And I suddenly realized that I knew everything in the book. That threw me. I couldn't believe it. I thought, how could this be? 68 pages and I already know this stuff? But I didn't know a lot of it, a few months before that. So that's what got me thinking, well, maybe I could do it. So the question is, why would I want to, right? Did you guys notice that when we were doing Alexander that I had a tendency to occasionally digress? If you think about it, what did I digress into? Every time Alexander came to a new place with new animals or new mountains or new fish, I remember when he got to the Caspian Sea, he was supposed to interact with a bunch of barbarians there and do some stuff, but I was more interested in the Caspian Sea sturgeon, the world's largest freshwater fish, right? So, you see what I'm getting at. I've always wanted to do this, but when asked, like I was asked by Deborah and some other people, well, what are you going to do next? I said, well, I don't think I'm going to do anything. I said, I'm not going to do Rome. I don't like the Romans particularly. I think they're a cross between Nazi Germany and the United States right now. I mean, I admire them. But I didn't want to do Rome. I love the Greeks. I don't love the Romans. What else could I do? Religion? That was interesting, but I kind of went through that back in the 90s, got it out of my system, and been there, done that. So what was I going to do? I couldn't think of anything. I said, what I really want to do is talk about science. But I can't talk about science because I'm not a scientist, right? Like, I take that kind of stuff seriously. I don't think people should get up and flap their lips if they don't know what they're talking about. Call me old-fashioned, right? I'm just an old redneck, I guess, but I mean, I don't think you should be standing up here BSing. So I thought, well, I can't do it. Now, I did have a bit of science at university, and I've been interested in studying all my life, but I don't have the degrees. And I also have to tell you that I'm not at home with chemistry and physics. So, this tonight is going to be mostly about a little tiny bit of physics. And just please understand, I'm only telling you what the books have told me. I do not have a deep understanding of physics or chemistry. But I hope I've got enough Yes, dear, you're making little motions. Telling me to get on with it? Okay, thanks. Okay, so that's why I'm doing it, because I'm interested in it. And I don't know if you can see this table or not, but what I started doing a couple of years ago was I started taking notes. And this is a table full of the notes I took. Okay, let me give you an idea of what we're going to cover in the course. We're going to cover from the beginning of life on Earth up until now. How are we going to do that? Well, obviously what we're going to have to do, and could you put up that zigzaggy thing, please? What we're going to have to do is we're going to have to pick and choose. Okay, so this is the poster, I guess, that we advertised with, and this is the beginning, and this is us now. Now, as you can see, this isn't life on Earth. This is how we got to be human, right? And I did say that in the poster, you know, how we got here. And there's two reasons for the accent on humans. One is that 99% of all the life that ever lived has gone extinct. But we're still here, so that's something to celebrate. And the other thing is that we're more important. I'm sorry to say that. I know that's not a popular sentiment to say, because a lot of people are trying to make the point, and I totally understand where they're at. We're not the only life form, we just act like it, right? It's that total selfishness and blindness. I completely get it. My point is this, that as humans, we're the ones that are wrecking it, and we're the only ones that can fix it. Nothing else. I don't care how smart dolphins are, or killer whales are, or wolves are, or octopus are. They're not nearly as smart as us, and they're not going to get us out of this mess. So, we're going to start with the beginning of life, and I guess probably end with us here as people. But I mean, on the way, it's the journey that's the fun, right? So just because we're not related to dinosaurs, like, I can see that probably I should have. Whoops. Okay, well, let's just work around it. You can see looking at this. Now, this is where, unfortunately, I can't read that, but okay, this is Tiktaalik. I can tell him. So that was discovered 375. That's 375 million years old, and it was discovered in Canada in 2006. So that's the fish from which we descended. Now that's 375 million years ago. This would be 415 million years ago. So we'll be starting up here at 4.54, the beginning of Earth, and working our way down to the present. And we'll be looking at what I think are the most interesting things. And also, the most interesting, thanks, son. It's my lecture, so I get to choose what I think is most interesting, right? And also most representative. So, I mean, if we're going to do the Mesozoic, we got to do dinosaurs because they were the dominant life form, right? And everybody loves them. It would be stupid not to. They're not related to us. We haven't been related to dinosaurs since 320 million years ago. 320, that should be right down in here somewhere. But we'll be looking at all the stuff. Like there's a great big mass extinction in here. It's really cool. And there's a snowball Earth up here and another one down here. And then there's the K2 extinction down here where the dinosaurs went extinct. So lots of stuff to look at. I think it should be a lot of fun. Okay, that's what we're going to do. Why am I doing it? I've already told you. Mark Twain said there are two reasons we do everything. The reason we tell other people and the real reason, okay? So the reason I should tell you, and it's true, is that science is under attack. A lot of people, for whatever reasons, either prefer not to believe it or try to falsify it. So I think it's time to defend it. I believe it. I love science. The other thing is that I'd rather talk about this than anything else, and that's the real reason. So there you go. So what we're going to do then, we'll work our way through. I want to emphasize the fact that everything changes. So this is about evolution. That's what that is. That's evolution. So it's kind of ironic because I'm going to use the Bible as a prop. I used to teach this. Isn't that funny? I mean, here am I. I'm talking about a course. It's nothing about evolution. It's nothing but evolution. I used to teach the Bible. Why not? This is the King James Version. It's the only thing ever put together by a committee that turned out beautifully. But my point here is that God says in chapter 1, verse 3 of Genesis, let there be light. So that's what we're going to talk about. Then, 14 verses later, he gets around to putting the sun in the sky. So we'll be talking about that kind of stuff too. But in between the first light and the first sun, there's quite a story. So it's that gap that we're going to be covering tonight. Now, I gave this lecture to Denise a couple of weeks ago, and we both decided that besides all the stuff about expansion and inflation and Heisenberg uncertainty principles, that we should probably include a few people. Because this is a story, right? What makes a story? You've got to have characters. And I don't care. Us people, we really care about other people. That's what we care about probably more than anything else. So we got to put some people in here. So what we're going to do is we're going to look at the science, and simultaneously we're going to look at the people who created the science, because what we're going to be covering tonight is we're going to be covering the Big Bang. I can't just start at Earth. That would be starting a story in the middle. So sorry, got to briefly go back to the Big Bang, tell you what happened there, show you how the first atoms formed, how the first stars formed, and then we get to Earth, and we'll be ready to look at the way Earth was when it was formed, and the first forms of life on it. So this is exposition, character, and setting. So, when is it? Well, you don't have to look at this, by the way. This is just for me. I mean, it's hopefully up here, or it's not going to work. This is just to remind me of what to say, okay? But anyway, 13.787 billion years ago, everything in the universe was crammed into a space. I have a prop for this. Okay. This is a really good little book. It's by Neil deGrasse Tyson. Astrophysics for People in a Hurry. Not dummies. I hate that. Astrophysics for People in a Hurry. Great little book. I read it about, 8 or 10 years ago when I had my first knee replacement, I think it was. Anyway, here's the point. See, you can't see it, but you can. You see that period at the end of that sentence?
Yes.
How small it is? Okay, so everybody can kind of see and imagine how small that period is, right? Now, can you imagine? I can't, but maybe you can. Can you imagine something smaller than a trillionth the size of that period? A trillionth the size of that period. Way smaller than an atom. Your average atom's a femtometer across. That's 15 zeros after a minus. This, the universe, was crammed into a space smaller than that. Now that defies my imagination. How about you guys?
Yeah.
But it defies mine. But that's what everything was crammed in. So, can you imagine how hot it was? The actual temperature was 10 to the 32nd power. So that is, I looked it up, and that's 100 nowillion degrees. So that's how hot it was when everything was crammed into a space smaller than a period. And when was it? We don't start at the Big Bang. We start after the Big Bang. And we start at Planck time after the Big Bang. We'll meet Max Planck shortly. Planck time is 10 to the minus 43. So that's where our story begins. After the Big Bang, 10 to the minus 43 of 1 second after the Big Bang. So all the stuff we're looking at is in like trillions and billions of seconds that we're talking about as this unfolds. Denise has put up a graphic to show you. Okay, here's what's going to happen. We're going to start out at the Big Bang. Gravity is going to manifest itself as a separate force, and everything that's crammed into that subatom size there is going to suddenly blow up into almost as big as it is now, and then it's going to stay like that for quite a while, and then after 9 billion years it's going to start inflating again, and that's where we are now. So tonight we'll look at the Big Bang and how things inflated, and as they did, those ridiculous temperatures got cooler, the size got bigger, and as the temperature and pressure went down, all the stuff that the universe is now made of started to partition out. That's what happens. So everything is crammed into one place. It's almost pure energy. It's also almost total order, so there's no entropy. And it's unbelievably hot and dense. And it can't stay like that because it's been pointed out for the universe to be in that kind of shape, be like balancing a pencil on its end. Can't stay that way. So what happened is gravity manifested itself as a separate force, and and what that did is cause a phase transition. Now I got to be careful here, all right? Just because I've learned all these neat new words, I've got to not do what they do on Wikipedia, which is to show how much you learn. I mean, how much you know, right? You ever notice the way people do that? I'm trying to learn something, right? I want to learn what an electron is, so I go to Wikipedia, and it gives me this unbelievable massive jargon. You know what I did? I went to the Particle Adventure. Remember that? I would be downstairs at night, and you thought I was hitting the porn. I was hitting the Particle Adventure. It's a site for kids, and it tells you all this stuff. It's totally cool. Anyway, so the universe blows up. Gravity establishes itself. So we're going to meet at... Oh, I got 3 questions for you I'm supposed to ask you. Number 1, how many people feel they know what an atom is? Please raise your hand. Don't be afraid.
Atom.
Atom. Just an atom. It's not a trick. If you think you know what an atom is, please put up your hand. Thank you. Okay, what about an electron? How many people could define an electron? Okay, good. How about an isotope?
Not really.
Okay, well, I'm glad to hear that, given you're a doctor. Okay, so, nice to see you. Okay, good. That gives me an idea. I think we're pitching it just about right here. I used Denise as a guinea pig, but unfortunately she's sort of smart, so I got to kind of test it out. But yeah, we're good. Okay, so what we're going to look at, we're going to see atoms develop as we go through. We're going to see the 4 forces that make everything in the universe develop as we go through. So by the time we get through, and we're going to have to, I'm going to really have to move it now, no digression. We're going to be at the Earth that it is now. You are going to know what atoms and isotopes are, and electrons and protons and neutrons. Nothing really complicated. Well, at least nothing once you know it. And then by the end, we'll all be, hopefully, on the same page. I'm not trying to be patronizing here, but just want to make sure that everybody understands a basic vocabulary. You don't need to know anything much in the way of physics or chemistry for this course. I felt I had to learn some because I'm the one teaching it, but other than that, I don't think you do. So, there are 4 forces in the universe. Gravity is the one that everybody thinks they know about, and yet, as we'll find out, this is the one force that nobody knows anything about. They're still trying to find what makes gravity work, and they don't know. But we'll look at what Newton thought of gravity, and then what Einstein thought of it, and see what it is now. So, for the present time now, let's just say what gravity is, and it's an attraction between 2 forces. So gravity establishes itself. We have 3 forces still in the mix, but gravity's kind of separate now. And we've got the first particles probably trying to form, but it's still too hot. They don't have any mass yet, and nobody's really forming much of everything. Now, I'm going to stop this part in just a sec. I just want to point out that in that primordial mixture, there were little tiny clumps. That's all I'm going to say about that at the present time, and then we'll come back to it. All right. What I thought we should do is, as a way to see how we got the science that let us know that the universe is expanding and that it was once very tiny and that it's getting bigger all the time, and that led us to all the knowledge we have, like about dark energy, dark matter, and all the rest of it. Those ideas were already extant in the ancient world. So you've all heard of Pythagoras, right? Okay, the theorem guy. Well, he lived in Italy with a bunch of Greeks, and they wore white robes and sandals, and they weren't allowed to eat beans. And Pythagoras said the world is round. So about 500 BC, he was the first to say that. One of his pupils, Philolaus, said the Earth is turning on its axis. Okay, so coming out of ancient Greece, we got a round world turning on its axis. Aristarchus, yeah, there he is. Aristarchus, about 2,430 years before Jesus Christ, said that everything is made, I beg your pardon, said that the Earth is going around the sun. Most other people thought the Earth was at the center, but he said, nope, the sun is at the center and the Earth goes around it. Democritus, who lived about 430 BC, said everything is made of atoms. Isn't that something? There's your first atomic theory. What does it mean? Atom, not cuttable, because he thought that these were fundamental particles, right? Okay. He also looked up and he said, those are stars up there, the Milky Way. Everybody else said, no, they're not. They're gods, you idiot. But he said, no, I think they're made out of the same stuff that everything is down here. And he was joined by that by Anaxagoras and Anaximander. Anaximander came up with the first theory of evolution. He posited that we're descended from fish. And indeed, this one, discovered in Canada a few years ago, is the closest thing we're descended from. We actually are descended from that. Wait till we get to that fish. You're going to love it. If you look at the fins, oh, wait a minute, I'm digressing. Sorry. But if you look at the fins, our arms are in those fins. You can see them. You can see, this thing has got a bunch of phalanges here. You can see our fingers. You can see our metacarpals and our carpal bones. There's a radius, there's an ulna, there's a scapula for and what's this one? The ulna. No, humerus. They're all there. They're all there 375 million years ago. So, gonna be cool. Anyway, so out of the ancient world then, what are these good ideas we got? A round Earth, spinning on its axis, with the other things going around the sun, just like it's supposed to, made out of atoms, with the heavens being made out of the same stuff as the Earth. These were some of the good ideas they came up with. Well, Aristotle didn't believe them, and the ancient world, do we have a picture of Earth? Okay, anyway, Aristotle nixed most of them except the sphere bit, and so the next thing that happened was the Roman Empire took over from the Greeks, the Roman Empire fell, the church came along, took the stuff that the Roman Empire took, which was all the wrong ideas from ancient Greece, and transmitted them through the Middle Ages as religious dogma. I'm not trying to be nasty, but the religion said, okay, it said, for instance, it's a great chain of being. This is how the world is organized. God is at the top, then there's 10 ranks of angels up in heaven, seraphim all the way down or whatever, and then down on earth you got the king, he's the head. Over in the animal world, you've got the stag, he's the head, or the lion, he's the head. Over in the vegetable world, you've got the oak tree or whatever. And in the animal world, you've got the lion, and in gems, you've got diamonds and gold. And that's how everything was set up. It was this hierarchical universe. And that's the wrong ideas, the non-scientific ideas that came out of the ancient world. All right, now we're going to get 1543. Moving right along here. Oh, that's not the number of the slide, huh?
No, I know.
Okay, Denise
Don't
knows
worry.
this stuff pretty well. If you've got any questions, address them to her. In 1543, Copernicus. Oh, what number do I want? Just a second.
Don't
10.
worry
Number
about it,
10.
dear.
Okay, that's Nicholas Copernicus. It wasn't his real name, but everybody in those days took Latin names. Like, it wasn't enough to be a scientist in those days. You had to write your friggin' science up in something like Latin or Greek. Can you imagine? I can't. I took Latin for 3 years. I'm actually glad I did, but that way I've got a good excuse for not understanding French. But anyway, what happened to this guy, Nicholas Copernicus, was that on his deathbed in 1543, he put out a really important book in which he said definitively and beyond the shadow of a doubt that the Earth was the center of the solar system. Everything else was going around it. And if you don't like it, too bad, because I'm dying. So that's what he did.
No, sun is the center of the
Yeah, what did he say?
Earth.
Oh, did I? Oh, thanks. Okay. He said the sun's the center of the universe, and then he died. Nobody could do anything to him. But let's look at Bruno, number 12. Now, this guy's a contemporary of Galileo. He said the same thing that Anaxagoras and Anaximander did. He said, everything out there is probably the same as here. And there's no reason to think there's any different laws. There's probably other suns and other planets. There might even be other life forms. Well, they burned them at the stake in 1600. So, the church was serious about the dogma. Now, yeah.
Were these just theories that
Sorry.
they had? They're theories that these men had. They had no scientific
That's
proof.
right. But
They're
questions at the end, okay?
Yeah, questions at the enemy. I'm my own worst enemy for digression. So if you guys ask questions, I'm really sorry, right? So so they burned Bruno because he contradicted church dogma, which they took extremely seriously. Galileo had to be aware of that. Now Galileo Oh, interestingly enough, he was born in 1564, same year as Shakespeare. To me, everything revolves around Shakespeare. So 1564, Shakespeare is born, so was Galileo. And he died on January the 8th, which was the same day that Einstein was born. Isn't that something? Yeah. Anyway, so Galileo died January the 8th, had this telescope. They had invented a microscope in Holland not too long before. Then they found that if they grounded a different way and pointed it a different way, it became a telescope. So Galileo had made a telescope, ground the lenses themselves, turned it up to the sky, and what did he see? He saw the sun. Okay, that's fine. But what did he see? He saw spots. Sun's not supposed to have spots. The sun is supposed to be a perfect orb. It's perfect, it's eternal, it's unchanging, and it's set in the heavens. Up in the heavens, nothing changes. Up in the heavens is where you hear the music of the crystalline spheres. It's got luminous ether in it, around which light is transmitted, and the happy gods whose blood, well, it's not blood, it's ichor, are enjoying themselves up there. And meanwhile, everything's supposed to be perfect. Galileo turns his telescope and he sees big pimples on the sun, sunspots. Then he looks at the moon, which is supposed to be a crystalline sphere of pure whatever, and it's got mountains and craters all over it. Holy smokes. And then Saturn, rings around Saturn. Okay, what the church has said is that everything up there is perfect and unchanging. But what Galileo is seeing is things are changing all the time. And instead of being this perfectly ordered bunch of perfect circles, nothing is in perfect circles. And this guy, Kepler, number 11, sorry, hon, put it out in a book in the 1600s, one of the more important books ever written. What Kepler did was he improved on Galileo. He said, yep, the sun's at the center of the solar system, the earth and everything else revolves around it, but they don't go in ellipses. See, what happens if you look at a planet in the sky and you trace its movement in the sky, it goes along and then it goes like that. So the ancient Greeks had to come up with a way of dealing with that. So a guy called Apollonius invented the epicycle theory, which says, well, that's the way the planets go around the sun. Now, Copernicus still believed that, but Kepler didn't. So Kepler said, and it was right, and so this is true, the planets don't go around in perfect circles, they go around in ellipses, and nothing up there is lasting forever. It's just the same as it is down now. Galileo also looked at light. He was smart enough to realize it was a thing, and he tried to measure it, like how fast it went, but he was unsuccessful. He also didn't believe Aristotle. Aristotle said that heavier objects drop faster than light ones. And if I dropped a feather in this, the feather would take longer to go down. But of course, that's due to air resistance, right? So Galileo actually proved, without a vacuum chamber, that that's not how gravity works. He rolled a ball down a series of ledges and found that the smaller ones rolled just as fast as the big ones. And so, he was a cool guy. But he started going to parties and blabbing about what he was seeing. Wrong move. So the church came along, arrested him, put him on trial, found him almost guilty of heresy, and sentenced him to house arrest. So he died a lonely, blind old man in his house. Probably better than going up in flames, but wasn't very happy at it. This brings us to, you all know who Neil deGrasse Tyson is, right?
Yep.
Hi there. Oh, yeah. You don't know who Neil deGrasse Tyson is? Oh, yeah. I'm in deep shit. Oh, anyway, he's the guy that wrote that book that I showed you the period. He has that black African-American guy that's the science popularizer. Anyway, he's this huge Einstein fan. So they asked him, who's the greatest scientist of all time? Without hesitation, he said Isaac Newton, smartest man that ever lived. So I'm not going to try to tell you about what Isaac Newton did, because let me show you what happened. I went downstairs. Yeah, here it is. I said to Denise, I'm going to go down and write down some of the more important stuff that Isaac Newton did. Well, I started writing. I kept writing. I wrote some more. This is just on Wikipedia. I wasn't even writing everything. I finally gave it up. But let's just address with three things: light, gravity, and motion. In terms of light, Newton had, oh wait, let's look at the apples first. Okay, 1665, Cambridge University is shut down. Newton can't go because there's a plague, right? The plague used to come through England all the time, bubonic plague. The good thing was that next year there was a giant fire and sort of sterilized it by burning down London. But anyway, Newton's at home. He's been sent home, so he's at home in Woolsthorpe. Looks at the tree. He claims this is true. The apple didn't hit him, but he saw an apple fall. And he thought, I guess along the lines of Anaxagoras and Anaximander and those guys, and Bruno, that hey, as above, so below. Whatever is making that apple fall to the ground is the same force that's making the moon go around the earth or the earth go around the sun or whatever. So every great scientist gets one great insight, right? So that should have been Newton's. Because just about every other great scientist in the world is great because she or he has had one great insight. But Newton just had them one after another until 1720 when he finally died. I mean, it's unbelievable. So, what did Newton do? All right. Oh, he was born on 2 days. He was born on December the 25th and January the 4th. 10 days apart. 2 birthdays. How did he do it? Any guesses? Okay, think about reformed calendars. Back in 45 BC, Julius Caesar reformed the Roman calendar because they were having March at Christmas. So it wasn't working out too well. So he hired a Greek guy. The Greek guy figured out a new calendar worked pretty good. So from 45 BC up until 1582, Europe had the Julian calendar. And then Pope Gregory said, no, we need a new calendar because this one's out by 10 or 11 days. So they got a new calendar. But then there's Britain. Europe gets a new calendar. The rest of the world gets a new calendar. What does Britain do? No way! So Isaac Newton was born in 1642 or 1643. Britain still hadn't adopted the new calendar. You know when they adopted it? They passed the Calendar Act of 1750. That's when they went on it. That's why Isaac Newton was born on 2 days. Okay, Newton is the guy that we think of when we come to gravity bit. I just wanted to show you the light bit where he shines light through the prism. So he cut a hole in his blind, let the light shine through it, put it through a prism, saw that it broke down into different colors, and was able, by taking the rays one at a time and putting them through other prisms, to discern that it wasn't the prism that was creating the color, it was an inherent property of the light itself. So a big step forward in identifying what light was. Okay, well, we'll come back to that. In terms of gravity and the apple, Newton said that the force of gravity is inversely proportional to the square of the distance. And with that, he gave us this beautiful law where you can figure out how far away, and do all this stuff with it. And it works beautifully. It's just that if you get into the realm of the very, very, very small or the very, 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 very hot, then it doesn't work quite as well, and you've got to go over to relativistic Einsteinian stuff. But for most everything, it works great. And the laws of motion. You've heard that for every attraction, there's an equal and opposite. That's Newton. He's the guy that gave us that. Oh, and the idea that if you get something moving, it's going to stay moving forever unless something stops it. All right. Over on the continent was the other smartest man in the world, Gottfried Leibniz. And Leibniz had a thing about light too, but Leibniz said, it's not, I forgot to tell you. Newton said light travels in little tiny packets called corpuscles. And Leibniz said, no, it doesn't. It travels as waves. So there was this big debate between the two smartest people in the world who lived at exactly the same time. And the other one was over calculus. Newton was so smart that when he was trying to figure out things like gravity and motion, he had to invent a new form of math to do it, so he invented calculus. Over on the continent, Leibniz was doing the same thing, but neither knew the other was doing it until they both finally found out, and then a most unseemly rivalry happened. Like, you'd think that people whose IQs were 200 would be mature. I'm not kidding, I'm not exaggerating, would be mature enough to work out their problems in a rational and mature manner, right? But no! Leibniz went back and fiddled with his own books to make it like he'd done things sooner, and Newton caused an inquiry to be held by the Royal Society into who invented it, and then Newton added in the comments about what a fraud Leibniz was. So they were both terrible. Anyway, that was their controversy about light. Is it a particle or is it a wave? This brings us to the last man who knew everything, Thomas Young. Yeah, there he is. By the time that guy was 14 years old, he was speaking 12 languages. And I mean, we're not talking easy stuff. We're talking about ancient Urartu and Hebrew and stuff like that. Young was really smart. Young came up with an experiment. There's one of the most famous in science. It's called the double slit experiment. Probably heard of it. Yeah, well, we don't have to go there. Anyway, what you do in a double slit experiment is you take light and you shine it through two slits. And there's this thing behind it, plate, and what you get is an interference pattern. You shine light through these slits, you shine it through two slits, you get these four patterns. The dim ones are, well, oh yeah, okay, I've got a thing here, I can write on the board. Okay, here you're throwing a stone in the water. The ripples are going out. See? When the ripples hit each other, they cause interference patterns. If they hit each other on the crest of a wave, you get a big wave. If they hit each other not on the crest, you get an interference pattern. And that's what Young got. So Young said there's no doubt about it. The only way you can get an interference pattern is if light is in waves. So, okay, great, it's settled. It's a wave. Let's move on. This brings us down to 1865 and James Clerk Maxwell, a scientist no one has ever heard of and which I'm going to rectify immediately. Maxwell in 1865 came up with 4 equations that he'd been working on for 9 years. And in them, he proved that electricity, magnetism, and light are all part of the same thing. Before that, they thought electricity and magnetism was separate. What Maxwell said, he said, nope. He said what light is and what electricity and what magnetism is it's electrical and magnetic fields at right angles to each other, propagating their way through space at the speed of light. I'm not arguing. How smart was Maxwell? Where's that scroll? Did you want to tell me something? I'm probably forgetting all sorts
I was
of
going to
things.
bring you the scroll.
Okay. So I thought I'd try to tell you what Maxwell did.
And don't forget, you're a Maxwell.
That's right. Anyway, forgot to mention my middle name's Maxwell. Not that's got anything to do with any of this, but I was going to try to tell you what he did, but we had this scroll made up. This is just some of it. Just some of it. So when Albert Einstein was visiting Cambridge in 1922, his guide said, oh, you must feel like you're standing on the shoulders of Newton. He said, no, I'm standing on the shoulders of Maxwell. So, I could pass that around later if you want. And so that you just get some sort of an appreciation for what that man did. The fact that his name is the same as mine has nothing whatsoever to do with anything. All right, what else? Yeah, and so Maxwell then, it's a wave, right? The other thing Maxwell did on number 22, he was also the first person to comment intelligently about the butterfly effect. He was one of the first persons to investigate control system chaos theory. First person to produce a durable color photograph. And as I said, a pioneer in control theory and cybernetics. Like, amazing guy. So, That's James Clerk Maxwell, the man who once again said that light was a wave. And now we're ready. We're almost up to the 20th century. We're doing well. I got 3/4 of an hour left, and I think I do, don't I, hon? Why are you going like that? Are you all right? You're going like this.
Move it along.
Move it along, baby.
Okay. All right, let's go over to number 24 then. This is neat. I can sit and talk at the same time. It's actually comfortable. All right, I said that I would try to give credit where it's due. There's some people who in scientific history have been left out. Some of them are women, so I'm going to rectify that situation right now. In 1908, that woman whose ancestors were Pilgrim Fathers, her name is Henrietta Swan Leavitt, and in 1908, she was hired at Harvard University as a group of computers. These women were called computers, just like, from let's show you like Star Trek. They was always saying computer, computer. Anyway, she was a female computer, and they were hired to work on what the men looking through the telescopes discovered. So the men operated the telescopes. The women weren't allowed to. Women weren't allowed to have degrees in science at most universities. They weren't even allowed to attend science at a lot of universities back in those days, just so you know how it was. We're looking at just over 100 years ago, and this is the situation. And that's something I wanted to emphasize. Almost everything I'm telling you tonight and in the entire series, they didn't know 100 years ago. Almost everything that we're sitting here knowing tonight, just taking for granted. We know what the stars are made of. We know the universe is expanding. I mean, we traced our whole evolutionary history back to the last universal common ancestor 4.3 billion years ago. We didn't know any of that 100 years ago. None of it. When I graduated from high school, they'd only figured out the genetic code 7 years before. So a lot has happened in the last time. So here's these women. They're at Harvard. The men are looking up through the telescopes. Henrietta Leavitt is assigned a certain class of stars called Cepheid variables. That's a Cepheid variable. Cepheid variables have bright periods and dim periods. To make a long story short, Henrietta Leavitt figured out all by herself that there was a correspondence between the brightness of the periods and the length of them. And using that, she was able to establish that if you knew the brightness and the period of that star, that you could tell how far away it was. Now just think about that. Up until now, nobody could measure anything more than about 100,000 light years away because they had to triangulate it. But with this, you could go way beyond that. So Henrietta Leavitt then made these Cepheid variable stars into what are called standard candles. You can look at one, and using it, you can figure out where all the other stars around it, how far away they are. And they still use that to calculate, even to this day, the rate at which the universe is expanding. It's expanding at 70 kilometers per second per megaparsec. So you take 70 kilometers per second, and then you have to multiply that by 3.26 billion. And that's how it's expanding. So these guys that I'm going to talk about right now are the ones that figured that out. Okay. So in 1927, so there's Henrietta Leavitt. She gave us a way of figuring out how far things were in the universe. Okay. And now we're briefly going to talk about the other astronomers, and then we'll go to the physicists. But maybe we should look at number 35.
35?
Well, it was going to be Lee Mattray, right?
Oh, okay.
Isn't he 35?
I hope. We'll see.
Okay, this guy's a Belgian priest. Now, I'm going to go back. Okay, I've jumped ahead too much, but I just wanted to show you how this got started. In 1927, Lee Mattray is looking at Einstein's equations. I'll tell you about those in a sec. And he realizes, looking at the equations, that the way the equations are set up, I know I already did this once, but again, it's like trying to balance the universe on its tip. He thought to himself, that cannot be. It can't. These equations tell me that the universe is either speeding up or slowing down, that it's either going backwards or forwards, that either at one time everything was at one tiny place, and it's getting bigger. That's what it looks like. So Lemaitre thought to himself, okay, I'm going to call that the primeval atom. It's that point from which everything began. Because if these equations are right, everything is expanding. And if everything's expanding, I'll take it back to the beginning. So he wrote a paper, published it, nobody paid any attention. So nothing much happened at that time. Just keep that in your mind, okay? Okay, now from Henrietta Swan Leavitt, the next person is number 25, Vesto Slipher. Slipher made an amazing discovery in 1915. He was looking at a galaxy and he saw that it was blue shifted. If I say blue shifted and red shifted, please put up your hand if you think you know what that means. Okay, thank you. Oh, no, go ahead, sorry. I was just giving you a chance. But hands, blue shifted, red shifted? Okay. Could I have the electromagnetic spectrum, please, my dear? I'm sorry, I can't remember what. Oh, there it is. Okay, so thinking back to Maxwell here in the electromagnetic spectrum, here we are with our radio waves down here. They're about the size of a building. Then our microwaves, they're a few inches tall. Then the infrared get really small, and by the time you're up here, you're into the width of an atomic radius. So this is the electromagnetic spectrum. This is the part we see. This is Roy G. Biv, right? I love that. Red, orange, yellow, green, blue, indigo, violet. Roy G. Biv. The only difference between that and that is you can hear this part of the electromagnetic spectrum, but you can't hear this part. But if this part gets into you, it'll ionize your DNA and you sure know something bad has happened. So that's the electromagnetic spectrum. So Vesto Slipher looked at a galaxy and he saw that it was blue shifted. So what does that mean? Well, when a sound wave is coming towards you, okay, see this blue up here? See this red down here? This is where it's red shifted, this is where it's blue shifted. When it's coming at you, these waves get compressed, they get shorter, they become shorter wavelengths, and so they get compressed into the blue zone. That's what you see. If the light gets stretched out, then it goes the other way and it gets stretched into the red zone. And so that's how you can tell. It's so cool. I mean, you turn your telescope on something that's millions of light years away, and you can tell whether it's coming at you or going away by the color of the light that it gives you on the electromagnetic spectrum.
Like a train coming at.
It's like a car coming at you. Same,
yeah.
yeah. It's the same thing with sound. Oh, I'm not supposed to respond to that because you're distracted. Bad girl. Anyway, okay, so that's what Slipher discovered. And by a couple of years later, he discovered that everything except one was redshifted. So they're all going away except for Andromeda. And he was totally right. We're going to collide with Andromeda in another few million years. It is heading at us, but everything else in the universe is moving away. It's all redshifted. Okay. Okay, and he, no, that's good enough for them. By the way, he eventually made Henrietta Leavitt the department head, and right about that time, a Swedish mathematician, of all people, nominated her for a Nobel Prize. She didn't get it because she was dead. She died of cancer in the meantime. It's a drag. So Henrietta Leavitt, remember that name, please. I love this next guy, Harlow Shapley. He went to elementary school, didn't like it, so he quit. Then he decided he wanted to be a newspaper man, so he had to have high school. So he took 6 years of high school, 1.5 years, and then he was born in Missouri, Nashville, Missouri. Went off to the capital to go to university. He wanted to be a journalist. They didn't offer journalism until the next year. So he said, well, I'm here now. What do you got? He said, well, the first thing is this, and it was archaeology. He said, I can't pronounce that. What's the next one? And he said, astronomy. He said, I'll take that. Slipher ended up as the director of the Harvard Observatory for 32 years. I love it. He also ended up before the House Un-American Activities Committee, and he called them a bunch of brainless primates. Anyhow, he was involved in what is called the Great Debate, and the Great Debate was over this. Again, think about how much we've learned in the meantime. In 1920, the great debate was whether the Milky Way was the whole universe or whether it was any bigger. Okay, and he took the position that was the whole universe. He was wrong. And Edwin Hubble phoned him up on New Year's Eve in 1925 and said, "I just proved that the universe is expanding." And Shapley said, "You ruined my universe." Literally wrecked my universe. But anyway, he was a good sport about it. He was right about some things, and that was, he came up with the idea of habitable zones. Heard of those on other planets, right? The idea that other planets have habitable zones that make them fit for life. Well, he came up with the idea called the water zones. Okay, now the guy with a pipe, Mr. Intellectual, Edwin Hubble. Hubble, there's a Hubble law on account of Henrietta Leavitt's measurements. Hubble was able to finally decide by 1929 and announce to the world Hubble's law, which is that the universe is expanding and that the further you go out, the faster it's expanding. Okay, you've heard of the Big Bang? Good, thanks, I'm glad to hear that. The guy who named it was a man named Fred Hoyle. He's an English astronomer. He did it derisively. Like a lot of the most famous names in history were originally insults, like Gothic or, well, the Big Bang. Anyway, it turns out the Big Bang is right. Hubble was wrong, Hoyle was wrong, but he's the one that gave it that name. Now, we're ready to look at particle physics. Something that everybody just can't wait to do. And it would never, ever fill anybody with fear and loathing. But I thought you'd feel better if you looked at that face. That's Max Planck. He's the father of the quantum physics. In 1901, he wrote a paper and he said, okay, get this. Everything is fundamentally uncertain. And there's nothing you can know for sure. But with energy, the energy is emitted and absorbed as discrete quanta. Now that's an exciting sentence, right? So I'll say it again. Energy is absorbed and emitted in discrete quanta. I mean, I don't know how you can contain your excitement, but that is a really important statement, you know, even though you don't realize it. If you're someone like Einstein, you realize it, but if you're someone like me, it takes a while, right? But the idea here is that it used to be thought that energy could be emitted over any spectrum, but it turns out that it can't. When things get really hot and really small, it's only absorbed as quanta. So what a quantum is, singular quantum, plural quantum, a quantum is just the smallest measure of anything that you can have in a given system. So in a system like an electron, like an atom, okay, you got an atom, you got your nucleus, your electron. In a system like that, energy, which is distributed through the electrons, I'll explain this in a second, it sounds horrible, but energy is only emitted in little chunks. That's what I'm trying to tell you. It's absorbed and emitted in little chunks. Einstein comes along 4 years later, and writes a paper called the photoelectric effect, which again sounds really exciting. He shows that photons can knock electrons off metals. Big deal, you say. Well, it so happens that again, it's done as quanta. So Planck started talking about how energy is transmitted in quanta. Einstein said, yeah, not only that, but light itself is transmitted as quanta. So what does that make light? It makes it a piece of something. It makes it a chunk, just like Newton said. He said it was a chunk called a corpuscle. These guys all said it was waves. Now, Einstein, the second greatest scientist in history, is saying it's particles. So what is it? Well, in a minute, we'll get down to this guy. But first, let's just back up for a second and look at one of the pioneers, Ernest Rutherford. The reason I wanted to look at this guy, oh, that's not him. There he is. He worked in Canada for a number of years at McGill. And he did some really important work with another guy called Niels Bohr on developing atomic theory. So I just want you to know that we had a special chair which we created for him in physics at McGill University back around the turn of the century. And he worked with another guy whose name is Niels Bohr, number 32. Oh, Rutherford discovered something that's really important. Yeah, may not sound that exciting, but it's super important. Discovered that radioactive elements have a half-life. So if I'm a uranium atom, say I'm a uranium-235 atom, that would give me a half-life of 700 million years, 710 million years. What does that mean? That means that in 710 million years, half of my uranium has turned into lead. I looked it up, and all of the lead in the world, except for a little tiny bit called lead-204, was originally uranium. All the lead was uranium, and it's all decayed from uranium to lead. If it's uranium-238, which is the less radioactive kind, the half-life is 4.46 billion years. It's the same age as the Earth. But if it's the other kind of uranium, it's got a half-life of 700 million years. So, do you understand now? If you know something's got a half-life, and that enables you to tell how old it is. If there's half of it left, it's that age. If half of that's gone, it's that age. When half of that's gone, it's younger still. Right? It's beautiful. It's beautiful. It's just lovely. So, sorry, I shouldn't tell you how to feel. So, you got Rutherford, who discovered the half-life, and he discovered beta decay. So you're thinking, who cares? Beta decay, hon. It's my big moment. The prop.
It's behind you.
It's behind me.
Look behind you.
Behind me.
On the board.
Oh! Isn't that something? This, as you probably figured out, is a banana. And why would I be talking about it when I'm trying to talk about a guy about Niels Bohr, right? I mean, it's boring enough. But this banana, I'm talking about beta decay, okay, and Rutherford discovered it. Beta decay is going on in the sun and the banana. So, think of yellow up there in the sun. That sun, right now, is turning 600 million tons of hydrogen into 594.5 million tons of helium. And the only way that that can happen is if a proton can turn into a neutron. And that's what happens in beta decay. And that's what happens in this banana. You'd have to eat 1,000 of these every day to get as much radioactivity as you would just going in for an X-ray. And I think you have to eat more. Oh, the bananas are totally harmless. But there's beta decay going on in here as we speak. Neutrons are changing in. No, I think there's two types of beta decay, positive and negative. One of them gives you an electron and a neutrino, and the other one gives you an antineutrino and an anti-electron. I can't remember which kind is going on, but it's beta decay. And it's the same process that lets the sun shine. The first step in the sun shining in nuclear fusion is the changing of a proton into a neutron. Okay, so we're talking about whether light is a matter or a particle. Let's have De Broglie. This guy looks like an artist, but he's actually a physicist. Number 33. Thanks, son. De Broglie said, okay, this is what the deal is. Light is a matter wave. It's a wave, it's matter, it's a matter wave. Light is both a particle and a wave, okay? Fine. Now, that was in 1924. In the same year, this guy, number 34, quite a name, Satyendra Nath Bose, wrote a letter to Albert Einstein. He said, hi, you don't know me? I'm a physicist over here in India. And I was just looking at Max Planck's derivation of black-body radiation. And I think I figured out a new statistical way of interpreting that. So I've got 5 pages of equations here that I've enclosed. And I'm thinking, if you think this is any good, could you please translate it into German for me and present it? He said, like, me and my buddies over here, we've been learning German and French and English because we've been studying what you guys are doing over in England. But they won't publish me because I'm a nobody. So Einstein looked at it, and he, being Einstein, A, caring about science more than ego, which I like, and B, realizing that there was something deeper here, said, sure, I'll do it. So we presented it, and Bose became an internationally renowned physicist overnight because of Albert Einstein. Bose and Einstein collaborated for the next 2 years, mostly by letter, And in the end of it, in 1926, they came up with a prediction that if you made a certain kind of matter cold enough, that all the individual bits of that matter would behave as one. That is called a Bose-Einstein condensate, which is as exciting as its name. And in 1995, people finally discovered one. Isn't that cool? So 1926 to 1925. Bose and Einstein, I love it. What I like about Bose is that even though he was a world famous physicist, in India, what did he do in his spare time? He organized working men's clubs and went out and gave lectures on nuclear physicists to guys who worked for a living. I really like that. Just the idea of taking knowledge and spreading it around. I gotta admit, I'm a sucker for that. I think that's the best thing. So back to Lemaitre, number 35, the guy who started it in a way. So he was looking at Einstein's equations on relativity. Oh, by the way, I really should mention a couple of things about Einstein. Let's look at Einstein and that. That's it? Okay, good. Einstein took Newton's theory of gravity. He said, well, that is a great theory, and it's been just fantastic for 200 years. First rate. He loved Maxwell's equations, too. He was studying those extensively as a young man. But he said, unfortunately, what gravity really is a warp in space-time. Space and time are a fabric, said Einstein. They pervade the universe, and what gravity is, it's mass bending space-time. Newton said it's an invisible attraction between two objects, right, or two or more. Einstein said no. What's happening is that a heavy object like an apple or the earth or the sun makes a dent in space-time, and other objects come along and they'll rotate around it, and they'll keep rotating if there's enough angular momentum, and if there isn't, they'll go right into it. So that's what gravity is, according to Einstein. And everybody accepts that now, but we still think of it as an attraction between forces. Like when I'm trying to hike up some stupid hill, I don't feel like I'm warping space-time. I just feel like somebody's got a hold of my feet. And it's, come on, feet, don't fail me now. You ever hear those? Yeah, me too. I used to have dreams like that. They were in cement. So Lemaitre then in 1931 put out another paper on how the universe was expanding, and this time people were ready to hear it. Okay, we're just about at the end now. You get there's light at the end of the tunnel, because that's what we're talking about. We're showing how light was thought to be a particle, light was thought to be a wave, then it's a particle. Well, you know what we know now? It can act as either. If you put it through a double slit experiment, it'll show up as a wave. But get this. If you think, okay, light, I'll trick you. I'll plug up one of those slits. It still does the same thing. Go figure. Give it one slit, it seems to separate, go around, and interfere with itself. It is just weird. And then on other circumstances, it acts like a particle. But it's not matter, because matter has mass and takes up space, and light doesn't. Finally, Heisenberg and Schrodinger. You've heard the names probably, right? Anybody watch Breaking Bad? Woo! Remember Heisenberg? I don't know why I called him that, but it was a real Heisenberg, and I can put in a nutshell why you should care about Heisenberg. This is what he said. Heisenberg says you can know where something is, or you can know how fast it's going, but you can't know both. Isn't that weird? So, under Newton's law, if I'm heading to Kamloops and it's 100 kilometers and I'm doing 100 kilometers an hour, you know that in half an hour I'll be halfway there, and in 1 hour I'll be there, right? Long McQuaid phoned up, said your new guitar's in, and I'm there. Heisenberg said, okay, under Newton's way of thinking, you can know exactly where L is. But if L becomes a photon, or an electron, or a proton, or some subatomic particle, you can't know where L is anymore, because he has now become a cloud of probabilities. That's what happens. In the quantum world, there's no such thing as knowing exactly where something is and knowing how fast it's going. All you can do is create an equation that will give you the probability of finding L. And when you look for him, if you find him, great. If you don't, you got to start the whole thing all over again. He could be anywhere between there and there. It's just probabilities. Schrodinger to the rescue. Schrodinger comes along, 1925, same year. Yeah, there he is. He brings in this thing. This is called psi, PSI. That's a Greek symbol, and that is a wave function. And Schrodinger said, okay, that equation represents everything you could know about a quantum system. All that means a really small system like an atom. Quantum, it just means what's the charge, what's the spin, how fast it's going, where is it, anything you want to know. You can figure out if you know how to do these equations, and if you're really smart, which I'm not and can't. You take that psi, which is a symbol, that's your wave function, and if you square the modulus of it, you can get the you can get the amplitude of the probability density of finding an electron somewhere between here and Kamloops. That's what the Schrodinger equation lets you do. It takes some of the uncertainty out of the fact that at a very small level, everything in the universe is uncertain. Yeah, I know, I don't blame some of you, but you're holding up really well. And our last guy is Paul Dirac. Paul Dirac was a nice guy. He figured that Satyendra Nath Bose never got a Nobel, despite all the important work he did. So he called the boson after Bose, and that's why we call them bosons. So where are we then looking at our little universe atomically and bosonically? Know this, there are two types of particles. There's one kind that regular matter is made out of, and those particles behave just like particles should. If you take them to a hotel, they all get their own rooms, and everybody's good. But there's another kind of particle called a boson. Bosons don't obey the same law. What's Pauli? Can we show Pauli? Is he number 31? I can't remember. I don't think he is, no. 39. Wolfgang Pauli came up with the Pauli exclusion principle. He told you what I'm just telling you right now. He said there's a type of particle where you can only put one in one place at one time. There's another particle where you can put as many as you want in the same place at the same time, believe it or not. And the ones that go in the same place at the same time are called bosons. And the ones that don't are called fermions. You don't have to know that. Just know there's these two different kind of particles. And why we care about bosons is the photon is the boson that makes electromagnetism work. So the next time you turn something on or off, it's your photons in there. They're the force that is making your electromagnetic force work. Gravity-wise, we don't know. It's a complete mystery. Nobody's found a gravitron. But the other two forces are called the strong force and the weak force. And the strong force is what holds the nucleus together. It holds the protons together. And the other force is the weak force. And that's the one that lets the banana and the sun operate. So those are the four forces of nature. And you've got two main kinds of particles, the kind that make up atoms and the kind that make atoms work. So you've got your bosons and your other particles. I hope that's okay. I mean, it makes sense to me, but everything makes sense once you know it, right? I'm not very good at learning a whole bunch of stuff at once. I'm not. I'm serious. I mean, I need a break. It's all I do, but I do need a break, and I find that I just can only take so much at once. So I apologize to you. I'm probably throwing a lot of terms at you, but I wanted to show you the people that did the science as well as the science, all right? So now we've looked at the people. I've got 15 minutes exactly to do the Big Bang. And it should be done in 15 minutes or less because you guys are tired. I really put it to you, haven't I? Hey, this has been non-stop. Please come back. Okay, in the Big Bang, that's 10 to the minus 43. Everything's squished into one place. What's going to happen is gravity liberates itself. We undergo a phase transition. What's that? A phase transition is where you got water in your stove. You turn it on, it boils. Water's going from a liquid to a gas. That's a phase transition. Why do you care? Because it releases energy. What's the big deal about that? Because the universe is all about energy. Life is all about energy. Everything is about energy. Life is a competition that's played out in various different ways, cooperatively, parasitically, all sorts of different ways to get energy. So everything in the universe is trying to get energy and conserve it. It's a law. It's called the conservation of energy. And the reason I'm mentioning it is that a huge amount of energy is released every time there's a phase transition. So energy, universe starts to blow up. We're going to need balloons in a minute.
Balloons.
Hey Claire, this is it.
It's party
I'm going to
time.
do a prop thing here, right? Should have done this earlier, but we'll do it right now. What happens is the universe blows up. And remember I mentioned there were little clumps? That's the last thing I mentioned. I said, okay, clumps, then we're going to go on to the people. Okay, so when the universe was all mashed together in a tiny little place, everything was in little clumps. Well, as it expanded, those clumps got bigger. Now what we've done is we got some balloons, and these are Canadian balloons, as they should be. We're going to push Canada as much as we possibly can. Now what Denise has done is she took these balloons, every one of these is one of those original clumps. Remember how tiny it was when the balloon was small? Well, now that the universe is inflated, all the clumps have got bigger. That's all I'm trying to do. So that's how to think of it. There's no center to the universe. There's no place that the Big Bang started. Now, I don't understand this, so don't, please look as puzzled as you want, because I am too. The Big Bang started, it wasn't an explosion. There was no noise. There couldn't be noise because there was no matter. There was nothing to make noise with. Matter of fact, there was no space for any matter to be in because there was no space either. Everything was crammed in that one tiny space. But then everything blew up, and all those little tiny clumps became great big huge clumps. So, at a certain point, the clumps became the size of fundamental particles, like quarks and electrons. Then they became the size of atoms, then molecules. Then they became the size of, stars after 100 million years. And then after that, galaxies. And that's how we got here. Those little tiny clumps that were there to begin with expanded as the universe expanded, just like that balloon. And that's why we've got all the structure in the universe. There you see it. Okay? As the universe spreads out, the clumpy parts get clumpier, the non-clumpy parts get emptier. So you start out where everything's almost the same, and then you end up there. So the universe expands. Just remember that as it expands, things are getting colder. And by colder, I mean they're only a few quadrillions of a degree. I mean many quadrillions of degrees. So the universe is expanding. We're going to cut it short. Bosons, which you know, now appear. And the Higgs boson shows up and gives everything mass. It was predicted in 1964. It was discovered in 2012. We were watching the program. I think this is where we show Penzias and Wilson. Pigeon poop. These two guys were working on the horn antenna there in New Jersey, I think it was, back in 1964. They were working with weather balloons and satellites. They kept getting interference. So they went up and they trapped all the pigeons and they cleaned all the pigeon poop out. But the interference persisted. And this interference was coming from all over the place. And it was coming from a very long time ago, it seemed. So they phoned up some guys over at Princeton who were working on a thing called the cosmic microwave background. And those guys said, well, you've discovered it. We've been looking at it for all these years, and you buggers have just stumbled on it. Anyhow, that's what it is. Now, it was predicted when the Big Bang was first predicted, it was said there should be something left over from when that happened. And what happened was, actually, I shouldn't tell you this quite yet. Sorry. They were working, 1964, these guys are working in Princeton, New Jersey. What they've discovered is evidence of the Big Bang. Because, I'll get to that in a minute. I jumped ahead, I shouldn't have. What I'm going to tell you now is we got that bosons, we got the Higgs boson, particles are forming, they're getting mass. This is the quark epoch. In the quark epoch, quarks. All a quark is a fundamental particle. So's an electron. If you put three quarks together, you get a proton. If you put three quarks together in a different way, you get a neutron. That's all you have to know. Protons and neutrons are the nuclei of atoms, and electrons are what? go around the nuclei. So quarks are fundamental particles that were created early on in the universe. They're really tiny. They can't be split up into anything else. They're fundamental, just like electrons and neutrinos. And they're what go together to make up the nuclei of atoms, and we're all made up of atoms. And all the universe that we can see, everything from whales to stars to us, is all made up of atoms. That's called baryonic ordinary matter. The other kind of matter is fermions, bosons. They're the ones that make it all work. So regular matter and bosons. Okay, quarks then are made here. Then after that, but by the way, as matter's being created, so is antimatter. Antimatter. That was predicted by our friend Paul Dirac back in 1928, the guy that gave the boson its name. He said they're going to discover this stuff called antimatter, and they're going to discover stuff called antiprotons and anti-electrons, and 4 years later they did, and he got a Nobel for it. So you've got quarks, they're the fundamental particles that make up nuclei. The quarks are surrounded by electrons, and all these things are out there forming, and they're all annihilating each other. Literally, for every 1,000,000,001 quarks, there's 1,000,000,000 antiquarks. 1,000,000,001 quarks, 1,000,000,000 antiquarks, so that there's one left when the annihilation ends. So things are annihilating like crazy. And finally, at 3 minutes after the Big Bang, one of the biggest things in the history of the universe happens. Things get cool enough, they're down below 1,000,000,000 degrees. Things get cool enough below 1,000,000,000 degrees that the first atomic nuclei can form. And all the atomic nuclei form in about 3 minutes. All the atomic nuclei that were ever going to form in the universe and make the first two elements, hydrogen and helium, they all formed in 3 minutes. Because before that it was too hot, after that it was too cold. That was the window. So, by the end of 3 minutes, you've got the protons and the neutrons, you've got the quarks coming together as protons and neutrons, and the protons and neutrons coming together as nuclei. And these nuclei form the nuclei that will become atoms 380,000 years later. By the way, these things kind of show you how everything, right here we are, everything's one. You can see how it's expanding. You can tell how old the science is by what they say. Let's just see, when does it say stars formed? I can't see. Anyway, things have changed a lot in the last few years. A lot of things are really dated. Anyway, what we've got now is nuclei. I know. Let's show the periodic table and show that. Oh, I'll tell them how that. Oh yeah, Penzias and Wilson, cosmic microwave background. Okay, so those two guys were working. They discovered the cosmic microwave background. Let me take you back. Imagine you're driving along in your car with your parents. You're in the back seat. It's many years ago. Maybe you guys never went through this, but we had to. I'm old. Driving along late at night looking for a motel or something. You got the radio on. And between stations, you get the static. Well, we never used to want the static, right? You wanted the radio station. But the static is the best part. Because it turns out that some of that static you hear between those stations on the AM is the cosmic microwave background. It's there, and you can hear it over that radio. There's a young lady back there, I think her name's Laisa. She interviewed me. She's really cool. She had some good questions. And she said, why are you doing this? And I'm babbling away like an idiot about, wonder or whatever. But when I think of something like that, it really does I get goosebumps all over my body. Oh, let me tell you this. Imagine you're listening to something that happened only 380,000 years after the Big Bang. That's 13.787 billion friggin' years ago. You can hear it on your radio. Right? Let me tell you another neat thing. In 1969, a meteorite fell near Murchison, Australia. So they did an analysis of the meteorite. There are in that meteorite things called pre-solar grains. And remember I told you about half-lives and how you can radioactive date things? Well, they dated these pre-solar grains. Some of them are 7.5 billion years old. That's 3 billion years older than the Earth. And it was found right on this Earth. So when Lacey had said, well, why do you do this kind of stuff? And I was trying to say, well, you know, it's kind of wonderful. When I think of holding in my hand something that's 7.5 billion years old, that fills me with, I don't sure call it wonder or whatever, but it's fantastic. And that's why I care about this stuff. So anyway, there's the cosmic microwave background. You can hear it. So what happened at 380,000 years was you got your first atoms. Quarks in the middle, electrons going around, improbability clouds. That's how it works. And so all we have to do now, and I've got 2 minutes, I'm going to tell you about how the solar system started. Maybe I'll tell you that next week. But you might not come back after what I just did to you. Like, I really am sorry. I know that was a lot of stuff. Yeah, basically we got 1 minute, so I think we can go through the solar system in no time.
Tell us about the stars.
Oh, the stars! Okay.
Yes.
So at 380,000 years after the Big Bang, you got your first atoms, right? The universe is still expanding like crazy. As it expands, those clumps get worked on by gravity. So the part that gravity is working on, the clumpy parts, they get compressed and agglomerated into certain confined areas. So after the universe has gone on for 100 million years or so we're looking at a considerable period of time right now, the universe is spread out enough and become clumpy enough that the clumpy parts have got hot enough to undergo nuclear fusion. So you got to get a temperature of around 10 million degrees to get nuclear fusion. So once things have been mashed together enough, you get stars firing up. And I will tell you more about stars at another time because they go through lifetimes just like people do. And like some people, they blow up. And when they do, they change the universe. This is where we do our periodic table magic. And then we can call it quits for the night. Periodic table. Let's have a look at the periodic table empty. Please?
I'll try.
Good job for me. You've basically memorized that. Okay, that's what the periodic table looked like before 380,000 years ago. I could have done chemistry. You know? I wouldn't have had to go to summer school. That's how it looked up till 380,000 years. Now let's look at it, the one with the 3 elements, please. I think it's number 40 or 41. That's what it looked like at 380,000 years. Now, the stars fire up, and we're going to look at it. What did the stars do? Let's look at it again.
You want it full?
Please, sweetie. Well, whatever number the full periodic table is, there it is. That's what the stars did. Before the stars, basically 2 elements. What did the stars do? They converted the hydrogen to the helium, and then not very much boron. Boron tends to disappear like beryllium. But carbon, nitrogen, oxygen, what happens is as the stars get to the end of their lives, what a star is doing is it's fighting a battle with gravity for its whole life. Gravity is trying to squash it, and it fights back by firing up and becoming nuclear. So the stars fight gravity by turning hydrogen into helium. Once they've used up all the hydrogen, they got to turn helium into the next thing up. And each time you turn it into the next thing, it becomes less and less efficient. So for small stars, the size of our sun, it's never going to make anything more than that. And when our sun dies, which it will in another 5.5 billion years, it'll become a red giant. It'll swallow the solar system, most of it. But we don't care, because Earth will have been rendered uninhabitable long before that. That's 5 billion years in the future. Life doesn't even have another billion years on this planet, because a bunch of other things are going to happen before that. That's how the sun will end up. And I think that's just about it for tonight. Is there anything else I should tell them? Let's call it quits. We'll do the formation of the Earth won't take very long. Honest to God, I can do that in 15 minutes, no problem. But then we're going to have to do. Well, I just hope you found it interesting enough that you'll come back. That's all. You know.